In this unit, we will discuss the concept of atomic mass, which needs to account for the fact that there are various isotopes for each of the elements and that they occur in varying percentages. As we discussed previously, the common unit for dealing with the atomic mass is the so-called atomic mass unit. The main reason for this is that the size of the subatomic particles is so small in terms of mass that we wish to use a convenient number such as 1 to do our calculations. So a typical conversion factor is that one atomic mass unit happens to be equivalent to 1.66 times 10 to the negative 27th kilograms. Turns out that the AMU is defined in terms of the mass of one of the isotopes of carbon. Hence the 1 AMU is 1/12 the mass of the carbon-12 isotope. So if we look on the periodic table, we can find some information inside of each of the boxes for each of the elements. We have the atomic symbol, in this case for sodium. Sodium is element number 11, so the atomic number is 11. There are 11 protons in the nucleus. The atomic mass, which is the number of AMUs for an individual sodium atom, is 22.9898. This also happens to be the atomic weight, which is the number of grams that would be for 1 mole of that particular substance. How is it that that number is arrived at? Well, it's the weighted average of all of the naturally occurring isotopes for that particular element. So I need to discuss how to deal with a weighted average. In this example of calculating the atomic mass for an element, we're going to be examining magnesium, which has 3 naturally occurring isotopes. There is one isotope which is a relatively low abundance, which is magnesium 26. This occurs as 11%, approximately 11% of the magnesium. There also happens to be a magnesium that has an atomic mass of 25. This is approximately 10%. And then finally, the most abundant isotope, which is magnesium 24, which is approximately 80% of the magnesium that occurs here on Earth. The relative abundances of each of these elements does change slightly depending upon your location, and that can be a really, really useful way of identifying the source of a particular sample, but these variations are extremely small. So, to determine the atomic mass, what we have to do is to sum together the multiplication between the fraction of the abundance for a particular isotope and the mass of that particular isotope. And in this case, in the table, we know the mass in terms of AMUs for each of the isotopes with quite a large number of significant digits. So we're going to take those into account. So there are 3 isotopes. So in this case, we're going to take the most abundant isotope and multiply 0.78994 times the mass of the magnesium 24, which is 23.9850417, and add that to the abundance for the second isotope, the magnesium 25, so 0.100001 times the mass of 24.9858369, and then add in the final isotope, which is the magnesium-26. So the abundance is 0.11005 times the 25.9825929. If you do the math and sum that all together, you come up with a number 24.30496. The significant digits, when we look back at our calculations, sig figs are limited by the number of sig figs in the abundance, and so there should be 5 sig figs in our answer. So hence we've underlined the 4, and since the next insignificant digit is a 9, we would need to round that up. So the atomic mass of the average atomic mass of magnesium is 24.305. And in fact, if you go and take a look at a periodic table, that's what you would find under the atomic symbol for magnesium. Turns out that one of the very useful modern pieces of instrumentation that can be used to determine the relative amounts of the various isotopes for elements and compounds is called a mass spectrometer. In essence, this is a device which generates a particle beam. We have a source of, in this case, it would be the magnesium atoms, and we heat up the sample, and these atoms start going into the gas phase, and then are focused through slits and are passed through a remove the electrons so that it becomes magnesium ions. We then pass these individual magnesium ions through a magnetic field, and depending upon the mass to charge ratio of these atoms, they get bent at different angles. We then focus those beams of the various isotopes of those ions onto a detector, and by doing a little bit of calculations, we can get an estimate of the percent of the abundance for those particular ions. Of course, the heaviest ions will be deflected the least because they have the most inertia while passing through the magnetic field, whereas the lighter particles will get bent more by the magnetic field. So, turns out then that if we look at the relative amounts of these isotopes and plot the relative abundance versus the mass number, we would get a graph that looks something like this. And so from that information, we can come up with our percent abundances.